Welcome back to the Deep Dive. We're here again to unearth some fascinating insights from the information you've shared with us. Today, we're tackling a concept that, well, it sounds simple enough, but it can actually bring even the most powerful computer systems to a grinding halt. We're talking about the dreaded deadlock.
That's right.
You've probably felt its effects, an unresponsive app, maybe your whole system just freezes,
Yeah.
even if you didn't know the name for it. It's a real puzzle, isn't it? How these perfectly good programs can just get stuck, like, indefinitely, even when it seems like all the resources they need are available.
It really is. And deadlocks are absolutely fundamental when you talk about operating systems. Dealing with them is critical for system stability, for performance. So our mission today is really to demystify this whole concept for you. We want to give you some clear examples, a look at the strategies, or sometimes actually the deliberate lack of strategies that operating systems use. The goal is for you to walk away not just knowing what a deadlock is, but really grasping why it matters, for everything from your own PC right up to massive server farms.
Okay, so let's unpack this. At its core, what is a deadlock? You said it involves processes getting blocked.
Exactly. It happens when you have a set of processes, and each one is blocked because it's waiting for a resource.
Okay.
But the resource it's waiting for is currently held by another process within that same set.
So it's circular. Like A is waiting for B, and B is waiting for A.
Precisely. Or it could be A waits for B waits for C, and C waits for A. It creates this closed loop of waiting. Nobody can proceed.
And it's not just a slowdown, right? It's a complete stop.
A complete standstill, yes. An indefinite halt. And as the material you shared highlights, the operating system has this significant responsibility for managing processes and threads. And that explicitly includes deadlock handling for processes.
Because the OS is the one managing the resources in the first place.
Exactly. It's the resource manager. Think about limited resources. Maybe it's access to a printer or a specific file or a lock on a piece of data in memory. If multiple processes need more than one of these limited resources to finish their job, well, they can inadvertently create this closed loop of waiting. It's a fundamental challenge.
Okay, I think I'm getting it, but an example would really help. The source material mentions a classic one.
Ah, yes, the dining philosopher's problem. It's a fantastic thought experiment to really bring this to life.
Okay, lay it on us.
All right. Picture 5 philosophers. They're sitting around a perfectly circular table.
Got it. 5 philosophers, round table.
In the center, there's a big bowl of spaghetti. And here's the catch. There are only 5 chopsticks on the table.
Only 5, not 5 pairs.
No, just 5 single chopsticks. And they're placed between each pair of philosophers. So each philosopher has one chopstick to their left and one to their right.
Okay, tricky.
Now, to eat the spaghetti, a philosopher needs 2 chopsticks, the one on their left and the one on their right.
Makes sense. Need 2 chopsticks for spaghetti.
And the protocol they follow is simple. First, grab the chopstick on your left, then grab the chopstick on your right. Seems pretty straightforward, right?
Yeah, seems logical enough. What could go wrong?
Well, here's where it gets really interesting, and our source uses this exact scenario. Imagine all 5 philosophers get hungry at the exact same time.
Uh-oh. I sense trouble.
Right. So following the rule, each philosopher simultaneously reaches out and grabs the chopstick immediately to their left.
Okay, so every philosopher now has one chopstick in their left hand.
Exactly. All 5 chopsticks are now held. Now, what's the next step in the rule?
Grab the chopstick on their right.
Correct. So each philosopher now tries to grab their right chopstick, but what do they find?
It's gone because their neighbor grabbed it as their left chopstick.
Precisely. Their neighbor on the right is holding the chopstick they need. So every single philosopher is holding one chopstick, waiting for the other one, which is held by someone else who is also waiting.
And nobody can eat. And nobody can put down their chopstick because they haven't finished the get right chopstick step yet.
You've got it. They're stuck. Indefinitely delayed, as the source puts it. They can't eat, they can't finish, they can't release the resource they hold.
Wow. Okay, that's a very clear picture. So this isn't just some abstract brain teaser.
Not at all. It's a perfect, vivid illustration of how a seemingly sensible set of rules for resource allocation can lead to complete system paralysis.
And the chopsticks in our computers could be anything: files, printers, database locks.
Database locks, network connections, memory buffers, hardware devices, any shared resource. When you see a program freeze solid, or your whole system hangs, or a website database just locks up and stops responding, that could very well be a deadlock in action.
It really shows why deadlock handling is such a core concern for the OS. Without some way to deal with this, things would just constantly grind to a halt.
Absolutely. It's fundamental.
So Given that these deadlocks are, a real threat, what can the operating system actually do about them? How do we prevent these digital traffic jams, or at least manage them? The sources we looked at outline, what, 3 general methods? And you mentioned one might be surprising.
Yes, broadly speaking, there are 3 main philosophies, 3 categories of approach. First, you can use protocols to actively prevent deadlocks from ever forming or to avoid entering a state where a deadlock might become possible. Basically, ensuring the system never gets into that stuck state.
Okay, prevention or avoidance? Proactive.
Second, you could allow the system to actually enter a deadlocked state, but then have mechanisms to detect that it's happened and then attempt to recover from it.
Detect and recover. Reactive.
And third, and this is the one that often raises eyebrows, you can essentially ignore the problem. Pretend that deadlocks just don't happen in the system.
Wait, ignore it. That sounds, well, risky for something potentially system crippling.
It does sound counterintuitive, I know, but the source material is quite clear. This third option, ignore the problem altogether, is actually the one used by most operating systems, including Linux and Windows.
Seriously, Linux and Windows just ignore deadlocks. How does anything ever work?
Well, it's not quite that they never happen, but it's a pragmatic choice. Think about the cost. Continuously checking every single resource request to see if granting it might lead to a deadlock down the line, or strictly enforcing rules to prevent them.
That sounds computationally expensive, like really expensive.
Extremely. It would likely slow the entire system down dramatically. The performance overhead would be unacceptable for the vast majority of users and applications, especially given that full-blown deadlocks, while serious, aren't necessarily happening every 5 minutes in a well-designed system.
So it's a performance trade-off. The OS developers decided the cure constant prevention or avoidance checks would be worse than the disease for general-purpose computing.
That's a good way to put it. It's an efficiency choice. The OS basically says, look, constantly policing for deadlocks will hurt performance too much. We'll provide the basic tools like locks and semaphores, but...
It's up to the application developer to use them carefully.
Exactly. The source states it is then up to the application developer to write programs that handle deadlocks. This shifts the responsibility. It's a critical point for anyone building software.
So developers need to worry about things like always acquiring locks in the same order or using timeouts when waiting for a resource.
Precisely. Careful resource ordering, using timeouts, maybe designing database transactions carefully. These become application-level concerns, not things the OS is automatically handling for every single program. A complex database system, for instance, will have its own very sophisticated deadlock detection and handling logic built into the database software itself.
Okay, that makes a lot more sense now why the ignore strategy is so common. It's delegation, really.
It is, but let's talk about those systems that don't just ignore it. How do they actually avoid deadlocks? You compared it to a smart traffic controller.
Yeah, like one that knows everyone's route in advance. Is it like that?
It's somewhat analogous. Deadlock prevention is about making sure one of the 4 necessary conditions for deadlock just can't happen. Like maybe you say a process has to request all its resources at once or none at all. That breaks the hold and wait condition.
Okay, strict rules.
Deadlock avoidance is a bit more dynamic. It requires the system to have, as the source says, additional information about how resources are to be requested. It needs some foresight.
What kind of foresight? Like the program has to declare its intentions.
Essentially, yes. The text gives an example. Imagine the system knows process P will request first the tape drive and then the printer, while process Q will request first the printer and then the tape drive.
Ah, so it knows the potential conflict.
Right. With this advanced knowledge, often about the maximum resources a process might ever need, the system can analyze each resource request as it comes in. It asks, if I grant this request now, is there still a sequence in which all processes can eventually finish? Or could this lead us down a path to deadlock?
So it's constantly checking for a safe state.
Exactly. It considers the resources currently available, the resources currently allocated, and the future requests and releases. If granting the request keeps the system in a safe state, it proceeds. If not, the process has to wait, even if the resource is technically free right now.
That sounds very careful, very robust. But I feel a but coming. Are there downsides?
There are. The main one mentioned is low device utilization and reduced system throughput.
Because it's being overly cautious, holding
Yeah.
back resources just in case.
Precisely. To guarantee safety, it might deny a request and leave a resource idle, even if granting it wouldn't immediately cause a deadlock, just because it could lead to an unsafe state later. So your overall system might run slower because resources aren't being used as fully as they could be.
Another trade-off then, guaranteed safety versus potentially lower performance.
Always trade-offs in OS design.
Okay, so avoidance needs that future knowledge, which isn't always practical and it can slow things down. What about the other approach for systems that don't ignore deadlocks detection and recovery?
Right. So if you can't easily prevent or avoid them, you let them happen, but you keep an eye out for them.
How does the system keep an eye out? What does it track?
It uses specific data structures that are updated over time. Our source mentions a vector called available that just keeps count of how many instances of each resource type are currently free.
Okay, an inventory of free stuff.
Then two key matrices or tables. First, allocation. This shows exactly which resources are currently allocated to which process. Like process 3 has 2 printers and 1 tape drive right now.
Got it. Who has what?
Second, request. This shows what each process is currently waiting for. The source uses the notation request to J, which simply means process I is now requesting K more units of resource type J.
So, available, allocation, request. By looking at those, the system can figure out if there's a circular wait.
Yes, there are algorithms that analyze these structures, essentially building a graph of dependencies to see if a cycle exists. If it finds one, boom, deadlock detected.
But checking this constantly, didn't we say that was too expensive? That was the argument against avoidance, wasn't it?
You're absolutely right. That's the critical point here, too. Invoking the deadlock detection algorithm for every resource request will incur considerable overhead. It's generally too costly to do it all the time.
So how do systems use detection then, if not constantly?
A more practical approach is to run the detection algorithm periodically. The source suggests maybe once per hour or whenever CPU utilization drops below 40%.
Ah, okay. So check every so often,
Yeah.
or check when things seem suspiciously quiet. Like low CPU usage might mean processes are stuck waiting.
Exactly. A deadlock often leads to processes being blocked, so system throughput drops, and CPU utilization can fall. It's used as a potential symptom to trigger a check.
Clever. But checking only periodically. Does that make it harder to know exactly when the deadlock formed or who really caused it?
It can, yes. If you run detection infrequently, by the time you find a deadlock, the situation might be complex. The resource graph, as the source calls it, may contain many cycles. It might not be obvious which dependency formed first, and ultimately the source makes a good point. Each of the deadlock processes is a link in the cycle, so all of them jointly cause the deadlock. It's usually a collective issue, not just one rogue process.
Shared responsibility for the gridlock.
Mm.
Okay, so we've detected it maybe after that hourly check. That what? How does the system recover? Well, the source implies recovery follows detection, but didn't give many details. What are the typical options?
Right, detection is only half the battle. Recovery means breaking the cycle, and yeah, it often involves some painful choices. One common method is process termination.
Kill one of the processes involved.
Yeah, pretty much. You could terminate all the processes stuck in the deadlock cycle. That's drastic but effective. Or you could terminate them one by one, rerunning the detection algorithm each time until the cycle is broken.
How do you choose which one to kill first?
Good question. Systems might use different criteria. Maybe kill the process that has consumed the least CPU time so far, or the one with the fewest resources allocated, or maybe one that's easily restartable. It's complex.
Ouch. Okay, what else besides termination?
The other main approach is resource preemption.
Preemption, meaning you take a resource away from a process.
Exactly. You forcibly take a resource away from one process in the cycle and give it to another process that needs it, allowing that one to proceed and hopefully break the circular wait.
But wouldn't that process you took the resource from now be stuck or have its work interrupted?
It would. You'd likely have to roll that process back to some safe state before it acquired the preempted resource and then let it wait again later. So you lose computation time, you lose progress.
So recovery is basically about choosing the least damaging way to break the cycle, either by terminating processes or preempting resources, knowing you'll probably lose some work.
That's a very good summary. The goal is to restore overall system functionality, even if individual processes suffer a setback. It's about breaking that circular dependency to get things moving again.
Wow, okay. So we've really gone from the basics, what a deadlock is, that great dining philosopher's example, through to the different ways operating systems tackle it. We've seen prevention and avoidance, which are proactive but can be costly or require foresight. We've seen detection and recovery, which is reactive and involves making tough choices. And then there's the most common approach, surprisingly, letting the application developers handle it themselves to keep the OS lean and fast.
Absolutely. And that last point is really the key practical takeaway for most people, I think. While the OS provides the basic building blocks, the fact that systems like Linux and Windows often rely on developers to prevent deadlocks means understanding these principles isn't just academic. If you're building software, you need to think about resource locking, potential circular waits, maybe implementing timeouts.
Yeah.
It really highlights that complex dance between what the OS provides and what the programmer needs to be responsible for.
It explains why sometimes even well-written software can just hang.
Yeah.
It might be hitting one of these subtle deadlock situations that wasn't anticipated.
Precisely.
All right, that brings us to our final provocative thought for you, our listeners. Something to chew on. Given that most common operating systems essentially push the responsibility for deadlock handling onto application developers, what are some of the less obvious, maybe unexpected, practical consequences you might run into if the software you use every day, or perhaps software you're designing yourself, hasn't been meticulously crafted to manage its resources and avoid these stuck situations? Think about that and join us next time for another deep dive.